Today we'll talk about the how we measure the soil's electromagnetic property, and mainly we'll talk about the electrical property, so the permittivity and the electrical conductivity. So, and do you remember the scattering in the mechanical wave? So when your wavelength is similar to the scale of the particle, then you have the wave will feel that you have an interface, so that the wave can reflect or transmit depending on the impedance mismatch, right? Impedance ratio. So that's kind of that can be applied to the electromagnetic wave too. So here, for example, 보이니? 그래도 잘 안 보이네. frequency. 잘 안 보이네. Okay, so in the scale of the frequency, say that this is the kilohertz and megahertz and gigahertz, right? So 10 to the 3 hertz and 10 to the 6 and 10 to the 9, and in the water molecule, in this range, you have a pretty flat permittivity. The real value permittivity is about 80, and around 10 to the 10 and 10 to the 11, that you have relaxation like this, which is because of the orientation of relaxation. Water polarization. And orientational relaxation. And as you go towards the lower frequency, you have double layer polarization. Actually, it starts a little bit faster. Double layer polarization. And around 10 to the 7 hertz, so that's about 10 megahertz, 10 to the 7. When the frequency is larger than this value, so the frequency is larger than 10 megahertz, this is microwave region, and the wavelength is about 30 meters, and wave propagates in the media, in the soil media. And when the frequency is less than 1 megahertz, wavelength is, how much is that? That's around 300 meter. So the wavelength is very long. So in general, this wavelength is too high, higher than the device or the size of the soil specimen. So this shows the quasi-static behavior. And So we can interpret the electromagnetic behavior as an equivalent circuit element. So when we measure the electromagnetic properties in low frequency, less than 1 megahertz, then we can think the soil as a circuit element, like a resistor or capacitor or the inductor. Right? But when the frequency is larger than 10 megahertz, then you can think of the wave just propagate as a like a light, right? Or the laser. But so here, when the frequency is 1 gigahertz, what's the wavelength? Wavelength is around 30 centimeter. So above this one, the skin depth is almost 0. So skin depth means that the penetration depth of the electromagnetic wave. 안 보이면 앞으로 와도 됩니다. 앞에 자리 많아요. 하나, 둘, 셋, 넷, 5개. Okay, let's move on. Then we'll talk about the impedance and admittance. Say that we have a oscillating voltage that has the amplitude of V and exponential function of j omega t plus phase angle phi. Then we can split into j omega t times e to the j phi, right? And also the corresponding current. So current is driven by this voltage, right? So current is the result of the applied voltage, and the current will have the amplitude I, and also e omega t plus theta. So I times e j omega t times e to the j theta. And what's the definition of the impedance? Definition of the impedance is the cause over effect. So this is the cause, right? The voltage is the region, and the current is the result. So this is the effect. So then Vt over It, then what do you get? V over I times the exponential function of j omega t will be cancelled. So you have e to the j and phi minus theta. And this Euler form can be expressed as the complex number. So you have r plus jx. So you can express the impedance in the form of the complex number of the real value r and the imaginary value x. And here r is called resistance, and the unit is ohm, and x is called the reactance, and unit is also the same with the resistance. And because it's a complex number, we all know that we can draw the Z in the R and X space. And this will be phi and R and X. So the R is Z cosine phi and X is Z sine phi. Right? So this is so obvious. And the definition of the admittance is the reciprocal of impedance. So admittance, we use the Y, and it's also the complex number, Y star and Y asterisk, and 1 over Z star. That's G plus J B. So this is just another parameter that's developed for the calculation, and G is here is for the conductance, and because it's the reciprocal of the resistance, 1 over resistance, so the unit will be 1 over ohm. And B is susceptance. Also 1 over ohm. So impedance and the admittance. Then how these two can be related? Let's find the real value, the conductance, the G first. So conductance will be real value of the admittance, Y, and this is 1 over G star. So real of 1 over R plus Jx. Then we can multiply the R minus Jx to the denominator and the numerator. So 1 over R plus Jx and R minus Jx times R minus Jx. So this will give you R minus Jx over R square plus X square. So R square plus X square minus J X R square plus X square. So the G is R over R square plus X square, and the B, the susceptance, is the imaginary part of the admittance. This is minus X over R square plus X square. So this was just the definition of the impedance and admittance in the electromagnetic wave, or the in the electrical circuit. Then we'll talk about the L and the R and the C. So in the electrical circuit, we have a three component. One is the resistor, R, and the capacitor is the C, and the inductor is the L. So that's why we use the LCR meter to measure the impedance of the the circuit or the material to be measured. So the first one is the resistor, and resistor, you know that this is the symbol for the resistor, and this follows the Ohm's law, right? And it dissipates the energy. So when you apply the voltage, it flow the current, and through the when the charge moves, it generates the heat. So by the heat, it dissipates the energy. So it's kind of consuming the energy using the resistor. And the impedance of the resistor is just the real value. So it's just R. So this is the real quantity. And impedance of resistor is not depending on the frequency. So this is not variable to frequency. So it's a constant value. And when you look at the Ohm's law in discrete form, the R is V over I, and here the V is the potential difference, the voltage, and the I is the current. And in the continuum formulation, you have the rho equal to E over J, and here the E is the electrical field, and J is the current density. And when you look at the unit, the rho is the electrical resistivity, and that unit is the ohm meter, and electrical field is the V, the voltage over meter, and current density is ampere over the area, the meter square. So then let's assume that you have some cylindrical conductor, and that has the electrical resistivity of the rho, and the area is the A, and the length is the D. Then the resistor, let's just the blue one. Sorry, the resistance is material property times, and resistance will be proportional to the length of the conductor and inversely proportional to the area, right? And we can derive the same equation from the definition of the Ohm's law. The rho is E over J, and the electrical field is what? Voltage over distance, right? So potential difference over distance, and the J is the current over the area, so the I over area. So then you get, where is it? V over R I and A over D, that's R A over D. So basically these two equations are the same. So keep in mind that the electrical resistivity is material property. So it has unique value for copper, whether the size is big or small. But the resistance can change depending on the size and the shape of the material. And the power consumption is defined as the rate of energy transfer across the resistor. And the P, the power is, we use the capital P. And current time voltage, so V T square over R. And the unit is what? We use the watt, right? W, that's A time the ampere time voltage, or voltage square over ohm. This is the unit. question so far? 여기까지. 쉽죠, 여기까지는? Okay. The capacitor. And so, capacitor is, you can think of just two parallel plates, and in between there's no material. Let's assume that you don't have any material, so it's just free space, the vacuum. And when you apply the voltage, or the voltage to here, then electron goes to here and the other direction too. So then you have negative charge stored and also the positive charge stored in this capacitor, right? And the amount of charge that can be stored in this capacitor is, so the charge is epsilon times kappa prime times the voltage and A over D. So as you apply the more voltage, then you can store the more charges. Okay? So the amount of charge that you can store is proportional to the applied voltage, or the potential difference. And if you have a larger area electrode, then you can also store the more charges. And as the distance gets closer, you can store the more charges. So as the distance gets far more, if the distance increases, then you're losing charges. Right? So that's why you have this equation. And also the amount of charges that you can store is proportional to the material's dielectric property. So how the material can be polarized. So here, this is the free space. So then this value will be just the same with the E naught, because the relative permittivity will be 1. Right? But if you put some other property, other material like plastic or water, then that material can be more polarized, so you can store the more charges. So if the kappa is larger than 1, then by that much you can store more charges. Right? So in general, in the capacitor, you have a dielectric material, and depending on this, depending on the relative permittivity of this dielectric material, you can that decides the capacitance of the capacitor. Okay? And here the Q is so C times V. Generally, the charges that can store is proportional to the applied voltage and also the capacitance. So this parameter here in this equation, this part can be replaced with the capacitance C. So the C is capacitance, and that's the same with the Q over V. So this is the capacitor. This is kind of what? Reservoir or the tank. When you think about the water flow, this is the same with the water tank. So we can think of the charge tank or the charge reservoir. So charge can accumulate on the electrode. So when you apply the DC voltage to this capacitor, in general the current changes with time. At first, because the charge will have to store, so for that time you have a high current, but as time goes by it dies. So this is called the charging current. For two parallel plate, and you have a distance d between this parallel plate, and the area of the parallel plate is A, then the capacitance is epsilon naught kappa prime times A over D. For parallel plate type capacitor. So let's think about the capacitor first. So it takes time for charge to be accumulated. So during that time, once the charge is fully saturated, then you don't have any current going in and out, right? For the same DC voltage. What if you apply the alternating voltage? So if you change the polarity of the voltage, then now the electron should have to move the other side to charge it, right? So when you apply the AC voltage, then the capacitor, when you look at this here, the circuit, it seems like the current is flowing. So as the frequency increases, these capacitors will have no resistance for flowing the current. But at the DC current, because the frequency is 0, then this capacitor will have the infinite resistance. So we're going to derive that in soon. Let's move on to the next page. So let's analyze the current, which is the charge flow. And here, the current I is dq over dt by the definition. And the Q from the capacitance, so here the Q is C times V, right? C times the potential difference. So the capacitance times dVt over dt. And then we know that the voltage Vt can be expressed with the amplitude times e to the j omega t plus phase angle. So if you plug it C and differentiate, get the derivative with respect to time, then E V j omega and the e to the j omega t plus v. Right? So, when you don't have any capacitance in the circuit, let's say that you have only the resistor in the circuit, then the voltage and current are in the same phase. There is no phase delay or phase change because it has the sign function. Then let's say that if this one has the sign function, and because you have first order of derivative here, then this gets the cosine, right? So now you have phase shift, 90-degree phase shift because of the capacitance. And also you have imaginary part here in this equation. So let's calculate the impedance. Then what will be the impedance of the capacitor? Voltage over the current. So cause over effect. So then V is this one, right? And I is this one. So I think the V can be cancelled. So the only remaining is 1 over C J omega, right? From the equation. Then multiply the J and J to the top and bottom. Then you have minus J omega C. So this is the complex impedance of the capacitor. So here, if we write it again, 0 minus J 1 over omega C. At frequency omega, so at a certain frequency. So then, again, when the frequency goes to 0, so this is the DC case, then impedance will increase, right? So this will go infinite. And as frequency increases to infinite, C goes to 0. Right? So impedance goes to 0 means that there's no resistance for current to flow. Right? So here, so capacitor, if you have a capacitor in the circuit, then it plays a role for high pass filter. And the energy stored in the capacitor is defined as the 1 over 2 times capacitance times the voltage square. So this is the voltage, V. So far, any question? 여기까지. Or comment? So? 이거 배우니? 물리2에서? 배웠니? 일반 물리 때 배웠어? 안 배웠던 거니? 알았어. 알겠습니다. 안 배웠던 것 같아, 나도. Okay, so the last element, the circuit element is the inductor. Inductor also stores the energy. And this is kind of you can think of the coil. Right? Coil, and that has the current going in and out. Then you have magnetic field, which is pretty linear magnetic field created by this coil and this field B. And this magnetic field is constant inside the coil. Okay? So inside the coil is constant. Constant coil. And when you have a straight coil, it's called a solenoid. And if you have a donut-shaped coil, it's called a toroid. And from the Faraday's law, so this is a Faraday's law, the potential difference in time is d over dt, and the magnetic field integral, surface integral of the magnetic field. Okay. And here the current is actually proportional to this term. This is linearly proportional to current T. So we can use some coefficient L and describe this Faraday's law. The voltage times is voltage equal to inductance times dIt over dt. Here the L is inductance. The unit is H. It's called a Henry. So let's say that you have some conductor inside the solenoid, and you have a conductor inside that has the length of d and area of A, and you have the coil turning. The number of turns in the solenoid is the n, so n turns of coil. Then the inductance is mu naught n square A d. Oh, sorry, mu naught and mu real times mu real. So this is for the free space. And when you multiply the conductors, the magnetic permeability of the material inside, then you get the inductance for solenoid. Question? Then we can also calculate the impedance of inductor at a certain frequency W, the omega. Then using this equation here, voltage is inductance time di over dt. Then we can put the I as amplitude I times E j omega t times E j zeta. Then L time, if we differentiate the current with respect to time, then j omega and you have the rest of it. So then the impedance is the voltage over current. So this part will be cancelled. So you have only L, J, omega left. So also the inductor has the imaginary component only. So this means that when you apply the voltage in the current also will be phase shifted. Right? So when the frequency increases, goes to 0, then what happens to Z? As omega goes to 0, Z will be also 0, right? So at DC, it doesn't have any resistance. Then when you have increasing frequency, Z also will increase proportional to the frequency. Right? So that makes sense because you have a coil, but when you apply the only DC current, then this will just straightly flow, the charge will flow to through the inductor. But as soon as you apply an alternating current, then there will be some accelerated charges moving, so that you have a magnetic field created too. Then the impedance will increase. Okay, then let's summarize in this circuit, in this page. We have looked at the RCL, right? RCL, and we can have the complex impedance and complex admittance when the frequency goes to 0 and when the frequency goes to infinite. Okay. Let's just summarize it. So the R, in the case of resistance, R is just constant, right? And it's not a function of the omega, so the omega doesn't affect the resistance, the impedance of the resistor. And admittance is the reciprocal of this Z star, so 1 over R plus, and there's no imaginary part. So that when the frequency goes to 0, Z is still R, and as the frequency increases, still Z is the R, so it doesn't change. And for the capacitance, impedance of the capacitor is J minus J 1 over omega C. Then admittance, this is 0 minus. Admittance will be 0 plus J omega C. And as omega goes to 0, impedance will go to infinite and goes to 0 when the frequency goes to infinite. And the L, case of the L, 0 plus J omega L and 0 minus J 1 over omega L for the admittance. So then impedance will be 0 and impedance will be infinite. Yeah. So then when the frequency, when you have the capacitor in the circuit, when the frequency goes to 0, then R is the resistance or the impedance goes to infinite, so that this becomes like open circuit, right? And if the frequency goes to infinite, as the frequency increases, the circuit will feel like this short circuit. So short circuit and open circuit means that, let's say that you have two electrode and you have a material inside. Then without the material, if you just connect it like this, then this is the short circuit. And if you just break it apart and you don't have any conductor inside, then this is the open circuit. Okay? So open circuit means that there's an infinite resistor, so there is no current flowing. And short circuit means that there is no resistance, so that the current can flow to infinite. This is the same, right? Short circuit and the open circuit. Then let's think about the moving charge and relative displacement and the charge acceleration. And moving charge is captured by the conductivity, right? Electrical conductivity or the resistivity, right? Conductivity, right? And the unit is Celin per meter for the conductivity. And resistance R is the equivalent circuit element. This has the ohm for unit. And for the relative displacement of charges, that means their permittivity or the polarizability, right? So epsilon or kappa is the material property that reflects the relative displacement of charges, and equivalent circuit element is capacitor, right? The C and capacitance. And the unit of the permittivity is Faraday per meter, and this is a Faraday. And for the charge acceleration, when you have a charge moving at time varying velocity, then you have magnetic field induced. Right? So here material property is captured by the magnetic permeability, mu. And the circuit element for that is the inductance. And the unit for that is a Henry per meter, and this is the Henry for inductance. So let's think about the just very simple LRC circuit here. You have a L and R, and you have a capacitor C here. And when the frequency increases, so that when the frequency increases, let's use this one. When the frequency goes to 0, then what happens? As the frequency goes to 0, this will go to, the impedance of the C is going up, right? That increases to infinite, right? This becomes to infinite, so you can draw the circuit, and this goes to 0, right? So this will be just like a just normal wire, and you have a R that's constant no matter what you have frequency, and you have an open circuit, right? like this. So this is the case. So the capacitance and inductance. What happens when the frequency goes to infinite? That's going to be opposite, right? The L will goes to infinite, and the capacitor, the impedance of the capacitor will goes to 0. So you have open circuit and resistor and just a wire. So both open circuit. Question. Okay. Then let's move on to the next page. Let's say that we have this kind of circuit, that you have inductor, and this is the soil or the unit that you're planning to measure. Soil. In this case, as the frequency increases, the impedance of the inductor will increase. So this will act as a low pass filter. Okay? So this will act as a low pass filter. And you can also design the high pass filter using the capacitor. So that you can just put the capacitor in series with the sample, right? L and the C. So this is actually the same function that you use for the oscilloscope. So in the oscilloscope, have you used the AC coupling? So there is a DC coupling and the AC coupling, right? AC coupling is when you apply the AC coupling, it's like that you are putting the capacitor in series with the measurement unit. So this is the same with the oscilloscope. AC coupling. So, for example, when you don't apply this capacitor in the circuit, so then normal case you are just doing the DC couple. Then you have a DC offset and also the real signal, the oscillating here. Then as soon as you apply you add this capacitor in the circuit, then you're losing the low frequency term. So this will go to 0 so that you have a well balanced. But you're eliminating the DC noise here. AC couples case and only the DC couple case. And what happens in this case? You have a sample and you are putting the capacitor in parallel. So this is the measurement unit. What happened? At high frequency, as the frequency increases, what happens to the impedance of the capacitor? impedance decreases, right? So the current can flow very easily through the capacitor, right? So as the frequency increases, the resistance, if you think about the resistance or the impedance of this one, this will goes to almost zero, so that there's free way for charges to move. So charge wouldn't go to here. So as the frequency increases, frequency increases, current will flow in this direction, and this part will feel like this part is disappeared. So this can cause the measurement error when you don't do it properly, when you don't do the design of the circuit properly. 이렇게 질문. Okay. I'll just briefly show you, and then we're gonna do this one again on Thursday. Let's imagine that you have two electrodes, the parallel plate, and then you're putting the soil inside. So maybe like consolidometer. You're doing the consolidation, and you're measuring the electrical property in the soil, of the soil. And for that, your bottom plate is metal, and the top plate is another metal, right? Then you can measure the resistance and etc., etc. And in general, that the soil can be modeled as a capacitance and the resistance. So the combination of the capacitor and the resistor, like this one. And this is called a lossy dielectric model. So you have a R and the C, and this R and the C value will be converted to the permittivity and the electrical conductivity value of the soil. So we're going to see that on Tuesday, and how we can calculate the real permittivity and the imaginary permittivity from the measurement. So actually, and then probably I'll show you how to use this one too.